My work is about the production factors affecting the performance of bleached outward kraft pulps for tissue paper applications. Was work developed in cooperation of University of Aveiro and Cellulose Beira Industrial. Under the impact of booming internet and new media, pulp and paper industries are now confronting the pressure of profound adjustment. While the demands for printing, writing paper, and newsprint are declining worldwide, packaging paper, pushed by the rapid expansion of express delivery business and tissue markets, are substantially growing. Focusing on the theme of this presentation, tissue market grows approximately 3 to 5% annually and exceeded in 2017 37 million tons. Looking to these numbers, pulp industries are now confronted to improve and optimize their production processes in an economical, viable, and technological feasible way. As a competitive area, tissue market required pulps with distinguished specifications, especially as concerns to absorption capacity and organoleptic properties, such softness. Softness is generally recognized as being comprised of two components, bulk and surface softness. It's related to the smoothness, texture, and surface uniformity, and so that is very sensitive to protanding fibers or irregularities at the surface. Absorption capacity refers to the ability to absorb and retain water quickly, which is mainly dependent on the capacity to form hydrogen bonds by the surface hydroxyl groups of cellulose. It's directly impacted by sheet grammage, bulk, and internal void volume. Such each void is a potential storage space for a liquid. Length, strength, lignin content, and physical and chemical damage of fibers are four wood characteristics known to have a strong impact on tissue properties considered. Tissue producers also desire pulps with moderate intrinsic viscosity and low hemicellulose content. Low hemicellulose gives paper with less degree of hydratation and is recognized as being one of the most important parameters in this case of study. Coarseness, curl, and kink are three key morphological characteristics known to have also a strong impact on softness and absorption capacity. So, in this work, aiming to evaluate the impact of some production factors in these two final tissue properties, a series of industrial pulps were first selected using multivariate statistics in order to ensure that the final properties would be significantly different. After this, these pulps were mechanical properties, morphological aspects, and chemical composition of these pulps were determined according to these standard methods, and the softness and absorption capacity were determined using MTEC tissue soft analyzer, and the absorption capacity according to the ISO referred. Here it's important to refer that softness and absorption capacity were determined by preparing laboratory end sheets, mimicking tissue properties, mimicking tissue papers of low grammage, approximately 20 grams per square meter. After this, in order to confirm the relationships found for industrial pulps by multivariate statistics, some laboratory work was done and comprised a cook and bleaching step, Eucalyptus wood chips were cooked on a dual vessel MK digester with a temperature of 160 degrees for 2 hours with similar sulfidity and hydromodulus 4, and for a range of different active alkali charges. Unbleached pulps were then submitted to oxygen gelification and followed by 4 bleaching stages, 2 of them using chlorine dioxide, 1 with hydrogen peroxide and oxygen, and a final bleaching stage only with hydrogen peroxide. The modifications in bleaching sequences comprised an increase of 100% of hydrogen peroxide and sodium hydroxide charges in PO stage, and another with an increase of 50% in chlorine dioxide charge in the final D stage. A partial least square analysis was performed in order to explain the maximum covariance of a matrix A containing softness and absorption capacity values by a matrix B containing the mechanical properties and the morphological aspects. As we see, trustable results were found because the decomposition of a matrix B was then used to predict new values of A, and as shown, we obtain a correlation coefficient above 0.9 by prediction of softness and absorption capacities. Generally, various important scores under 0.8 are considered low, which means that these variables don't have a strong impact on the prediction of new values of softness and absorption capacities. Hence, the prediction of softness showed a negative correlation with the xylene content, with a correlation coefficient of 0.91, a negative correlation also with burst resistance, tensile strength, and elongation, and at the same time was positively correlated with coarseness and curl of fibers. Absorption capacity showed a negative correlation with the Gurley resistance, with a high correlation coefficient of 0.97, a negative correlation with intrinsic viscosity and the surface roughness. These tissue properties show the positive correlation with kink index of fibers. For laboratory-produced pulps, in general, the correlations found between tissue and pulp mechanical properties corroborated the conclusions drawn before by statistical analysis of industrial pulps, but a strong relation was also found between stiffness and softness, and between stiffness and absorption capacity. As stiffness is associated to the intensity of interfiber bonds, this negative correlation seems coherent and for absorption capacity, and for the same reason, softness was decreasing. As could be expected from these two trends, a positive correlation between softness and absorption capacity was confirmed with a correlation coefficient of 0.71. Fixing the bleaching sequence, an increase of cooking severity led to a gain of almost 6 Enfield units, similar absorption capacities, which was accompanied by a maximum loss of 5.3% yield, a decrease of 2.4% in xylose content, substantial loss of intrinsic viscosity values, and lower hemicellulose content. Fixing the cooking severity, modifying bleaching sequence affected negatively both softness and absorption capacity. When compared to standard bleaching, for each cooking severity, softness dropped 3 to 5 Enfield units in modified PO and 5 to 6 Enfield units in modified D. Lower absorption capacities were found, and as well as mechanical properties, with the modifying PO stage being the one with the highest negative impact on the mechanical properties. This decrease of 0.6% in xylose content. We'll talk in the next slide. In relation with xylose content, and taking in consideration the correlations found before for both industrial and laboratory-produced pulps, the intention of modifying PO stage was related to the better purification of the fiber surface and with the purpose to remove extensively hemicelluloses. However, and although effectively the xylose percentage in modified PO has decreased, any improvement in softness was detected. I will push the slide. And the correlation was, it have a strong negative impact on this correlation. This can be explained at least partially by a depolymerization of polysaccharides, and so a decrease of approximately 100 intrinsic viscosity units, which means the effect of fiber weakening. In short, with this work we conclude that eucalyptus bleached kraft pulps have a significant effect on on these tissue properties. Softness of ECF pulps were negatively influenced by xylene content and pulp strength properties. Absorption capacity showed high negative correlation with girly resistance, surface roughness, and intrinsic viscosity of industrial pulps. The relationships found for laboratory-produced pulps corroborated the conclusions drawn by industrial ones, and showed also a clear trend of softness and absorption to increase with the decreasing of end-shift stiffness. Severity of laboratory cook revealed an increase of softness and similar absorption values. Pulps showing better softness also revealed better absorption. Increase of reagent charges in bleaching stage affected negatively both softness and absorption values. And last but not the least, xylene removal or polysaccharides degradation in pulping and bleaching operation leads to a different effect on softness and absorption capacity. Thank you for your attention.
Very good. I'm very glad to be back in Portugal. Even though I'm based in Sweden, I have traveled quite extensively previously in Portugal. It's a lovely country, really. And in fact, my first business trip went to Portugal in 1987 when we introduced the first Kappa number analyzer. I will do this presentation together with my colleague, Renato, from our branch in Brazil. I would also like to thank Mr. Andreas Wikström from SCA Obbola Mill, where this example is taken from. He has also contributed to the paper. So SCA Obbola Mill is based in the northern part of Sweden, close to the coast. The nearest city is Umeå. And it's a high-yield mill. They make linerboard, Kappa number target around 80. And they invested in a new continuous digester in 2015 from a Swedish supplier. And the second part of the paper that Renato will do is about the possibilities of even further increasing the yield and the pulp quality using model-based advanced process control. So this mill, they had a batch digester plant, built in the 1960s. In 2015, they tore down the old batch plant, and they put in a new continuous digester. They produce around 260,000 tons yearly, but the nominal capacity is much more. And the reason for that deviation is that they are in the process of preparing for a new investment, a new board machine, and that the extra capacity will be utilized. So they are producing virgin pulp. They are also producing recycled pulp for the liner. So now I will start to talk about the first challenge in this project control-wise, and that was to even be able to measure the kappa number. Because you have the new continuous digester from a Swedish supplier. It is equipped with a control system, H-factor supervisory-based control. And what they lacked to stabilize the kappa number and to increase the yield was a continuous kappa number measurement close to the digester. Because you need that feedback signal in order to control the continuous digester to the desired kappa number. The challenge in this case was that the refiner is located far away downstream. So it's a matter of more than an hour between the refiner and the digester. And the challenge was to try to minimize that time. And the only possibility was to put the analyzer, the automatic kappa number analyzer, in the blow line. And one has to remember at this point, the pulp is not really defibrated. It's more chips than pulp. So that was the challenge. So this is taken from the internal screen system that is integrated in the analyzer. You can see the reject from the analyzer and the accept. And since all automatic kappa number analyzers are based on optical features, the absorption of ultraviolet light, it means that we cannot measure on big pieces of chips. We need free fibers. And the amount of free fibers is very small compared to the reject. So that was really the challenge. And what we used was this SPK, it's in single point kappa number analyzer. It's measuring the fiber kappa. It can also measure hexaronic acids, and you get also a fiber length index. It's a part of a new family of tools that we have to control and to optimize the fiber line. So we have, using this one on the brown side, digester and oxygen stage. We are using other tools in the bleach plant where we can measure all lignin in the fiber line. Fiber-based lignin, filtrate-based, dissolved, COD, in order to optimize a complete fiber line. In this case, there was no bleach plant, so only this one was needed. So this is how it looks like. We are using the single point kappa number analyzer to measure the lignin content of the fiber. We have other tools to measure the lignin content of the dissolved lignin in the filtrate, and also the total kappa number, fiber plus filtrate, together with brightness. That is used to optimize a brown stock wash and to optimize a bleach plant. But in this case, what we used was this tool, measuring the lignin content of the fiber. So we went from this technology. This was the one that I mentioned I was introducing back in 1987, the first automatic kappa number analyzer. It's a central unit where you take samples and you transport the samples to the central unit. What we have done now is that we have simplified that technology from this complex system into this more simple, more easy to handle system. So you use one analyzer for each measuring point. And actually I have still holding the patent for this measuring technology that we was introducing in 1987. So the analyzer is bolted, is mounted directly on the blow line in this case. So this is the blow line. It takes a sample, it screens, washes, measures, and cleans, all in one. No piping, no extra sampling valves. It's integrated in one unit. This is how it looks like. This is the product manager, actually, for the unit. So this is to give you a feeling for the size. So you can actually handle it by yourself. You can really carry it yourself. So this is the unit with the sampler built in, and the sample handling, and this is the control unit. And the benefits is that it's handleable, it's easy, simple, few components, have a high availability, and a very fast cycle time. It measures every 5 minutes. So this is how it looks like internal. You have the blow line, you have the sampling valve, and you have the drive unit. So this is the sampling valve. This is where the sample is collected. And you have the drive cylinder, and you have the control unit. You can see it here. And this is where the screening is taking place, the measuring, the washing. This is the drive cylinder, and this is the screen unit from another angle. So this is how it looks like in the mill, bolted directly onto the blow line. This is how it looks like during the measuring cycle. It's little bit low resolution, but you can see that there's quite some chives still in that pulp, but it's possible to measure. And what we did, considering this situation that we have with a high level of reject and very few free fibers, what it is all about is to optimize the internals of that analyzer. It's very similar to optimize a screen basket, for instance. You have to control the wire mesh, you have to control the flow, the directions that the fibers are coming in the flow. It's a little like floating timber. You want the fiber to come with a sharp end first, not to get clogged into the system. So it's about optimizing a lot of water nozzles. The bends should have a certain angle, a certain radius. So it's small things, but very important things, because if you don't do that, you cannot measure, and you lose the measurement completely. So what we have today is that it has been mounted here for more than 2 years. The maintenance is, we have a service contract, so we service it 4 times per year. The mill does not do anything extra, so we come every quarter to do a service. And it has been providing an accurate feedback signal to the supervisory system of the digester. And what one has to consider also when doing a project like this is that since the refiner is downstream, there is one factor to be taken into consideration, and that is that this reject, chives, knots, pieces of chips, when they have a higher average kappa number, lignin content, compared to the free fibers. So when they are passing the refiner, the average kappa number of that pulp is really increasing, because you have a lot of unreleased lignin that is freed when you pass the refiner. So when we measure with the kappa number analyzer, it's around 80. After the refiner, it's 83. This has been shown to be very constant, so it can be handled with an offset. So it has not been an issue in this case. So the result is that the mill, using that simple technology with the feedback, they have been able to increase the average kappa number at least 1 unit. And 1 unit doesn't sound a lot if it's 80 or 81, but it means a lot of money, actually. Because if you increase the kappa number by 1 unit, you increase the yield calculated on the wood consumption by 0.3%. In production, that is 0.6%, because the wood consumption is 2 times the pulp production. So at the current production rate, it means more than €1 million extra per year, calculating on normal, or actually got pretty low market price for the pulp. At the nominal capacity, it means around 2 million. And this has been done only with the signal from the kappa number analyzer. We are very sure that there are much more further potential if you can use an intelligent, advanced, model-based process control on top of that existing supervisory system. And that is what my colleague Renato will discuss. So please, Renato.
Good afternoon. My name is Renato Onofre from Brazil. My idea was to present this in Portuguese, in Brazilian Portuguese, of course, but let's go to in English, no problem. So I'm going to complement presentation from Sven Arne showing some ideas on how we could improve the process using advanced process control and real-time optimization. I know that time is now a little short, so I will try to be as fast as possible in here. So first of all, I'd like to show you a traditional instrumentation and controls pyramid, where we have at the bottom the analyzers, like the kappa analyzer Sven Arne presented, sensors, transmitters, like temperature transmitters in a cooking plant, and control valves. And on top of that, we have the real optimization. The intermediate layers, we have a regulatory control layer, like the DCS, and we have also another layer which is called advanced process control. What's the difference between this layer and this one? Basically, optimization has a cost function on it. So we optimize the process and drive it to achieve the best result as possible in terms of cost, production, whatever we want to achieve. So this kind of optimization uses a platform, optimization platform, with a similar architecture like this one, where we have the DCS controllers at the bottom. Can be ABB, a Valmet, whatever, DCS controllers. And we have an OPC connection to optimization systems. Usually uses a hardware, a dedicated hardware to process all the information. This kind of optimization uses the MPC technology, model predictive technology, which in practice combines controlled variables and manipulated variables in specific curves or models. Basically, some process changes are done, or the bump tests are done, so that we can build those models and based on that optimize the whole process. And it's my time, sorry about that. I'm going to be a little further in here. Another comparison between a regulatory control and MPC, it's a little small here, but a traditional regulatory control system uses the kappa information into a block and then to H factor on the digester. You can see that the alkaline ratio is not used in this case. In an MPC, much more information is used to optimize process. So for instance, we can combine the kappa analyzer with retention times in the digester. We can build soft sensors that will, inside a block, define the H factor and the alkali charge in different positions of the digester. So the complexity here is much more compared to this one. And of course, the end result is much better. Here's just an example of control matrix that we can develop during an optimization project, where we have some manipulated variables in here, controlled variables, and constraint variables, which limits the control action. So in general, we can, for instance, as manipulated variables, we can use the screw speeds in an IV and digester. We can use the alkaline ratios, liquid ratios, all the temperatures, and the blow flow. We manipulated those variables to achieve some stabilization, process stabilization in terms of controlled variables. So act here and control this one. And just to finalize, I'd like to show you some typical benefits. As Sven Arne said, the main idea is to increase yield, and how advanced process control can help on that. Basically minimizing the variability. If you have a kappa variability like this green curve, the idea is that we can reduce this variability to a curve similar to the gray one. And based on this variability reduction, we can shift the kappa to a higher target, like from 80 to 81 or 82. And by doing that, we improve yield, the cooking yield, that can be converted of more production or less wood consumption. And beside of that, we can also improve the white liquor consumption and steam consumption. All of this can be turned to money, this portion and this portion. Thank you very much for your attention. If you have any questions, I don't know if you have time, but anyway.
Yeah, we have some.
Okay, thank you.
Good afternoon, Pedro Matos Silva. 2 questions, one for each. What is the range of kappa number where we can apply this new technology? Is because you mentioned this experience in the 80 level, but can we use it in very much lower levels of kappa with the same accuracy? And the second question for the other colleague is these models that can be also used using other technologies, I suppose. So with the kappa analyzer like we have today, we can use these predictive models to apply them with the same results, I suppose.
Yes, thanks.
I can answer the first question. The nominal range is from kappa number 2 to 120. The issue when measuring with this technology is not really the kappa number itself, it's that we have to get enough free fibers. So the lignin content is not the big issue. The issue is to free the fibers so that we can measure the lignin. So, but the nominal range is from kappa number 2 to 120.
And answer your question, actually, that having an online instrumentation like a kappa analyzer, it helps a lot on optimizing the whole process. So, like the SPK delivers a kappa analysis every 5 minutes, which is very good for a feedback in a control philosophy. If we would depend on a laboratory information every 1 hour or 2 hours, it's not enough. So by combining instrumentation and MPC or APC, in general, the results are definitely much better.
So thank you very much for your kind presentation. Good afternoon, everyone. I'm going to show you just a small part of my PhD work. I started last year, so I have a few results. The project is called as Potential of Bleached Eucalypt Kraft Pulp for New Non-Papermaking Applications. So, as everyone told in the previous presentations, we have assisted to a decline in the graphic paper segment worldwide. So we have to look to, as a pulp mill and paper mill, we have to look for new products because, of course, we have the innovation, we have new technology, we have the new segment and new electronic device. They are going to replace the paper and the graphic paper that we are used to work. So it will be a challenge, but we have to look to the demand of the new product, so new challenge. We have a lot of examples of non-papermaking applications looking to the fiber. We have the packaging, we have medical non-woven disposable, we have the molded pulp. I brought this picture because it's a shoe that have molded pulp inside. We have baby diapers and, of course, tissue products. These are just few examples of non-papermaking applications. The first approach that we have done in my PhD was to look to a specific segment of a non-papermaking application, that is the fluff pulp. The fluff pulp is a kind of material that is made by using cellulose fiber with high absorbent properties. They are used to the baby diapers, to hygiene fields, incontinence products, so a large variety of applications. So the main goal at the beginning is to evaluate the potential of the Eucalyptus globulus for the fluff pulp production. The methodology will be evaluate the the chips, of course. We will do in the MCAP laboratory digester with different pulping conditions, and then oxygen, the lignification, and then to evaluate all of the bleaching sequences. And of course, at the end, try to modificate or transform the fluff pulp with biopolymers or additives. So in this work, we started with bleach hardwood kraft pulp and softwood bleach kraft pulp as papered. And they were the samples. And these samples were turned in small pieces and then introduced in the pilot scale hammer mill with a specific, a constant velocity of 3,500 rotations per minute. So at the end, we have a kind of material that was called the fluff, and then at the end we analyze the chemical and physical properties and, of course, the absorption capacity. So this pulp, the bleached hardwood kraft pulp, is from Selby. I show you here. Of course, the pulp line production, wood preparation, digester, screening, washing and oxygen, delignification, bleaching plant, and pulp machine and the finishing line. So all the pulp was collected here, and the pulp samples were bleached with two different sequences. We have the elemental chlorine-free and the total chlorine-free. The difference, of course, is don't have the dioxide, the chlorine dioxide, and has here a chelating stage before the peroxide stage. So the cooking and bleaching conditions. A series of 6 industrial pulps were produced from hardwood, were selected, and we pre-selected because we tried to pick different extreme conditions of pulping and bleaching. And of course, to have a comparative way, we choose a commercial bleached lobaline pine softwood fluff pulp that we call C1, that is used to produce fluff pulp. So the pulps H1 to H6, except the H4, they were bleached by elemental chlorine-free, and the pulp H4 was bleached by total chlorine-free. Regarding the commercial bleach lobaline pine, we didn't have enough information about the pulping and the bleaching conditions. So the methodology was to analyze, of course, all the parameters. In the pulp, before the defibrillation in the pilot scale hammer mill, we have done the paper properties, chemical composition, fiber morphology. After the hair defibrillation with the pilot scale hammer mill, we have analyzed the knots content, the fiber morphology, and of course absorption and retention capacity. So here we have the mechanical properties of the bleached pulps before the defibrillation, and we can see that they have similar extreme pulping and bleaching conditions, but we can see some difference between the hardwood kraft pulps, around 20 to 35% of different in the mechanical properties. And as we can see, the C1, that is the lobaline pine bleached, the softwood pulp, has lower mechanical properties when compared with the hardwood kraft pulps. So, in this slide, I have these two figures. We can see these figures that the dependence of the tensile strength and the tear resistance of the viscosity of the eucalypt. And what we can see is that the TCF pulp H4 is out of the tendency observed for the other for the other pulps. Probably most of these variations is due to the different degree of polysaccharides degradations during the pulping and bleaching conditions, and of course because we have, this is a TCF pulp, we have the last oxidative stage that has done the polymerization of the polysaccharides. And in this picture, you can see the importance of the dependency of the viscosity of pulps from the content of carboxyl groups. Regarding to the neutral sugars, we have done a characterization, and we didn't found a clear relationship between the xylene content and the amount of the detected carboxyl groups and pulps. And this can be explained probably by the importance of the oxidative bleaching stage, that is the O stage, and the peroxide stage in the formation of the carboxyl groups. So those slides that I show you, they were about the bleached pulp before the defibrillation in the pilot scale hammer mill. So then we compared after the defibrillation with the pilot scale hammer mill, and we have done the fiber morphology that is very important to the fluff pulp, special to the form and the structure of the fibers, because how much they can hold the water. It's a very important parameter. So as we can see here, the craftwood pulp has just a loss of around 10%. And then the loboline pine, the softwood, has around 70%. And this could be explained, especially of the high intensity of the defibrillation, because we used a constant rate of speed that I already told you about, 3,500 rotations per minute. Probably this pulp could be defibrated just with 2,000 rotations per minute. That's why we saw a huge loss in the fiber length. And of course, we saw a loss in the coarseness and an increase in the kink of the torsions. It was expectable because of the mechanical action of the hammer mill, and a huge increase in the fines content. So, regarding the knots content is the fiber bundles that are formed during the hair defibrillation or during the hammer mill pilot scale when we introduce the pulp in the hammer mill. So as we can see here, the knots content of the hardwood kraft pulps are very high compared to the softwood. This could be explained because of the density of the sheets. The density of the sheets were higher in the craftwood pulp, and were like half in the softwood pulp. And what we consider here as knots content was the part that was retained in this mesh that was around 12 millimeters. Regarding the soak and drip capacity, we have very interesting results in the soak capacity, because we see here that the craftwood pulp has a higher soak capacity than the softwood pulp. However, in the drip capacity, the softwood pulp has better results. This drip capacity is a water retention value, but not the ability. It doesn't measure the ability of the swelling of the fibers. It's just a retention capacity. And at the end, we could find a very interesting relationship between the retention capacity and the carboxyl groups. And of course, this is interesting because the retention capacity is the most closer to the water retention value that, of course, correlates very well with the carboxyl group. So this is a very interesting correlation that we found. And of course, that it's a huge advantage that the eucalypt kraft pulps have much better absorbency than the commercial softwood pulp. So as conclusions, with this study, the results were very interesting to understand and to evaluate the potential of the Eucalyptus globulus to produce this kind of material. Of course, that the cooking and bleaching conditions will affect the production of this kind of pulp. A very interesting result is the absorbency of eucalypt fluff pulp are at least 30% greater than the commercial softwood. And of course, this is a beginning of pH work. It needs a lot of improvement and more work to have more inputs and more results to sustain these conclusions. So at least I would like to thank to Selby Altri for this opportunity, to my supervisors Sofia Rei Jorge and Professor Dimitri, and my colleagues Michaela Santos and Joana. Thank you very much.
Nobody has questions, so I have one question to Sofia. I think this is really interesting because we are opening up new areas for eucalyptus pulp that till now were, let's say, more or less reserved to southern pine in US and some mills in Sweden. So the question is, looking at these results and looking at the segmentation, for instance, in the dye-appear business, how do you see the potential for eucalyptus fluff pulp in those businesses? Is there any application that you think that could be a way to move forward?
Mm-hmm. We know that we, mainly in the baby diaper segment, most of the fluff pulp is replaced by superabsorbent polymers. So, but I think that the globulus has a high potential in this kind of material because of the different parameters that we found regarding the absorbency and then the defibration energy. I think that it will have a huge potential when compared with the softwood, that is the commercial one and the more used worldwide.
Very good, thank you. Any other questions to Sofia? No? Okay, so I have one question to Joana. So we looked at what's your presentation. Of course, I have to confess that I was aware of some of the things that were said there. It's inside information. Nevertheless, what I feel is that this is a way, when we hear about Industry 4.0, this is a way to use big data besides just making tests in lab or industrial real plants. But I have one question to you, Joana, that is, we have different conditions there. We saw some interesting results for one of the most growing, the biggest growing markets, that is the tissue paper. How do you see the potential of applying what you've seen there, the conditions, in the daily life and don't jeopardize the economics of the pulp business?
Okay, so I think that as I show, the main relation we found was with the lower hemicellulose content, which is naturally represents a slight decrease in the yield. But here we are talking about laboratory results, and we need to go to the industrial scale and understand how much deeper we can go, and which are the best adjustments we need to do to optimize the production processes and turn it to in a viable way. But I think at this point we need to go deeper and understand exactly if the gain in softness and absorption that we show in laboratory scale if it is reflected by tissue producers and understand that after the creping processes, which we know that have a huge impact on these properties, if the difference are reflected on the final tissue papers.
Okay, very good. So if no further questions, I just want to thank and ask you for a big applause for our speakers.